Hello, everyone. My name is Rich Ottinger, and I am the Marketing Programs Manager for Park Systems. Welcome to the final installment of Park Systems 2020 Material Science Research and AFM webinar series. Today's presentation topic is flow chemistry. Before we begin, let me give you a quick overview of today's session. The presentation is expected to take approximately 40 to 45 minutes, which should allow us some time for a question and answer period at the end. If you click the raise your hand button at that time, I can unmute your line to ask a question. If you would prefer, you may type in your questions at any time during the webinar, and I will try to pose those at the end. Any questions that we do not get to, we will address in a follow-up email. It is now my pleasure to introduce to you Dr. Rigoberto Advincula. Dr. Advincula is a professor of macromolecular science and engineering at Case Western Reserve University and the editor-in-chief of MRS Communications. He is a fellow of the American Chemical Society and is the author of more than 250 peer-reviewed publications. Please welcome Dr. Rigoberto Advincula.
Well, thank you, Richard, and good morning, good afternoon, and good evening to all our attendees. And I hope you're keeping well and are productive, and at the same time having a balance of your priorities as I try to. I would like, first of all, to thank Park Systems for the opportunity to give this talk. As Richard said, this is the last from our series, Material Science and AFM. And for a lot of you who are followers, especially of AFM, SPM, and investigations using microscopy, I hope you found this series together with the other talks that I gave other than the AFM to be very useful in educating yourself in the area of material science, chemistry, polymerizations, and now with flow chemistry. So we do a lot of work at interfaces, but these interfaces translates to chemistry, and also the importance of techniques like AFM enables us to investigate structure, property, relationships, as well as investigate chemistry or processes done at the interface. Now, in our expertise, and I'm talking about our group, we work a lot on polymer materials, synthesis, characterization, and fabrication. Just to review the importance of polymers at interfaces and their role in colloidal phenomena, polymers are able to have order to disorder transitions, crystallize at surfaces. We can also graph them as polymers or even polymer brushes, all the way to thicker membranes, layer by layer order polymers, and bulk thin films. You know, a good example is a layer of paint, printed ink, which actually can be traced to its microscopic or even nanoscopic phenomena. On the other hand, what we see in emulsions, colloids, or different types of compositions that are viscoelastic, the use of polymers as they enable to be surfactants or even viscosity modifiers can also be traced in terms of their ordering as micelles, lamellae, or higher ordered complexes that eventually translate to macroscopic properties. So in other words, polymers play a very vital link to that structure property relationship. Now, what is of interest to some of you perhaps is in the area of synthesis, where you are interested in the sequence of monomers, topology, block copolymers that influence their morphology at surfaces. So called AFM, TEM are great techniques, microscopy techniques to investigate this morphology that is influenced by the architecture, topology, or even composition of the polymer. So macromolecular architectures are very important. The question really is, how do we end up with precise structures that we design perhaps on paper and end up with a polymer that we can study or investigate using this state-of-the-art techniques. Now, let me give you an overview of some of the polymers that we have made and investigations on surfaces through the years. Um, After all, I've been around as a professor since 1997 with a group that is focused on polymer and nanostructured materials. And so we have done through the years research including conjugated polymers, conducting polymers, different macromolecular architectures, including dendrimers and LED, as well as light harvesting systems. We are also well known in the area of dendrimer synthesis, where we can control the topology based on the design and the use of what we call AB2 type of monomers, in which case our focus had been in terms of doing electropolymerization and investigation of energy transfer and charge transfer properties on dendrimers. More recently, we have done a lot of work related to topology that is supramolecularly templated. That is, knots, catenanes, or different macrocycles or polycycles can be approached. And we have demonstrated that you can do this by leaving polymerization of these templated knots through complexes such as phenanthroline and metals. And that's how we reported the first polycaprolactone triple knot, for example. Lastly, we have done a lot of work on grafting of polymers on surfaces that are based on surface-initiated polymerization. We can classify the grafting of polymers as a grafting through, grafting from, and grafting onto. Again, a lot of chemistry that can be manipulated here and has shown practical applications in terms of adhesion, membranes, and sensors. So with this overview, my question is, how can we differentiate the synthesis of materials, polymers in particular, under flow conditions or flow chemistry polymerization? So just to give a backdrop on the interest of flow chemistry, a lot has been investigated in the area of microfluidics, microreactors, or the use of different flow conditions that somehow simulate what would be found in a large engineering project or in the realm of chemical engineers as they run plants that beyond pilot scale but production in petrochemical plants, for example. Now, all of this can be done in the bench scale by relying on controlled flow conditions with control of temperature, pressure, and even surface area. And as I said, this is a growing field in the area of materials or polymer synthesis because of that controlled environment. In fact, it relies a lot on control of mixing, either the use of passive or active micromixers, for example, in microfluidics, has been well studied to affect the kinetics of a reaction. So modeling, including AI, is ripe for optimizing such flow conditions, and the investigation of flow chemistry can focus in this area, which includes the design of new devices, microfluidic systems, or chemistries that can be done under flow conditions. How does this stack up with a traditional material synthesis? So for those of you who are chemists, you are more attuned, perhaps going back even to an undergraduate, that a reaction can be done on a flask or a container where we essentially mix the ingredients, whether it's a monomer, an initiator, or two reagents and a solvent. We then rely on complete mixing to isolate the product, separate it from the reactants, and then characterize it, and then after characterization, purify it and go to the next stage. So there are several differentiating factors that type of reaction is not amenable towards controlled synthesis. Whereas this diagram shows that if we simply have a flow condition, let's say where we mix the reagents or reactants 1 and 2, and then we control the mixing as well as the environment of mixing, that is temperature, pressure, and flow rate, we are able to isolate the product, and as I'll show you, in high yields, precise synthesis, different types of combinations that allow us to control the kinetics of the reaction, but more importantly, put the control in your hands as a process parameter rather than simple mixing. So as shown here, this enables you, for example, under this flow condition, to control these environments, including thermal transfer, the application of flow conditions in a column that is embedded with catalyst, as well as introduction of a gaseous monomer. So more of this differentiation, you can see that the surface area, the flow nature, the control of that heterogeneity can be done under flow conditions, very different from a simple batch reaction or mixing. Now, this is not entirely new. In fact, as a materials chemist, we benefit from what has been done even in the pharmaceutical industry. So when organic chemists talk about the conditions on a flow reactor, they get all excited because they know the value of this. For example, in asymmetric synthesis, where one has to control the enantiomeric excess or the different types of enantiomers that one is able to obtain, for example, to synthesize a drug or a drug precursor. On the other hand, this is of interest to them as well, meaning the pharmaceutical chemists, in order to increase the yield so that they can use more of the same stuff for the succeeding reactions and therefore increase the overall yield. So this is, for example, shown in this hydrogenation reactions on these intermediates to give you the final conversion product, let's say with high EE in the case of the reduction of this ketone to the corresponding alcohol, or below in terms of the coupling reaction to provide you the this coupled intermediate product. Well known in pericyclic reactions in that you can apply light or heat in order to have a cycloaddition reaction as shown here. Therefore, controlling the EE, the yield, as well as the orientation has been shown to be quite efficient in the application of flow process parameters, including the use of microreactors as shown here. Now, the Wittig reaction is a well-known reaction to form, let's say, steel beams or double bonds coming from lead and the different phosphine reagents. This has been demonstrated to have very high percentage yields when done in a reaction flow system, or even the use of redox chemistry to control the reduction or oxidation of reagents where an applied field together with the flow conditions give you higher conversion rates. In the area of particle synthesis, so phase separation where one is able to introduce a separate phase, let's say a hydrophobic polar and a non-polar fluid, and of course they phase separate. One is able to control the dimension, the size, and the rate by which particles are produced, or in this case, all droplets. Now, this can be, of course, translated to a polymerization setup where actually particles or monodispersed microparticles are produced. So let's say what is represented by oil and water simply means that the oil can have a resin or a monomer and an initiator that can be initiated to produce particles, which are then individually isolated and as shown here with very good monodispersity. And the size, the rate of production, the degree of cross-linking or polymerization perhaps can be as simple as controlling the flow rate. And there are many examples of such value chain in particle synthesis. Now contrast this to, for example, reactions in a colloidal suspension or emulsion polymerization to produce latex particles. They have their advantages and disadvantages, yet the chemistry of mixing can be applied and uniquely with phase separation to control the dispersity as well as the composition of these systems. Microfluidics applied, let's say, in the case of micelles that can then be stabilized by polymerization or cross-linking. And it has been shown here that flow rates, for example, can be used to control the degree or size of this nanoparticle. So this type of control on the size, for example, is not easily achieved in a stabilized emulsion polymerization, whereas this can be easily controlled by controlling the ratio, flow rate, or even temperature and pressure parameters. Gas phase polymerizations or reaction are hard to control, yet in the case of a gas and a liquid that can be equilibrated by a Teflon membrane, this means that during the reaction, a gas monomer or a gas diffusing reagent can be introduced together with the liquid by controlling the pressure or intrusion pressure between the inner tube and the outer tube of a membrane. So this type of control has been demonstrated and has been shown to be quite accessible compared to simple batch flow reaction conditions. And the gas phase reaction, for example, is another way to safely do hydrogenation or deuteration. In that case, the hydrogenation allows you to have very good mixing ratios as well as safe introduction of the gases that allow, for example, the hydrogenation of these different double bonds. So with all those examples from monomer synthesis to polymer synthesis, let's look at some of the work we had done to demonstrate the viability of reaction under continuous flow chemistry compared to that of a batch reaction. So again, the advantage here is the environment by which mixing or the entropy is controlled based on the degree and the confinement of space by which you do the mixing. Ergo, what happens is that you are able to control the heat diffusion or the thermodynamics as well as the kinetic control more precisely compared to a batch by simply confining your reaction where the reagents mix at the mixing juncture. Thus, with that control, one is able to continuously feed the monomer and initiator or the two reagents. And as long as you continuously feed the reaction, you are able to isolate the product. Hence, one of the advantages of a continuous reaction or polymerization setup is this is akin to turning on the tap and getting continuously, and stopping the tap allows you to just simply turn off the reaction and stop the production. Hence, if you don't turn off the tap, then you'll continuously produce the product. So why are we interested with this in the area of polymerization? So as you can see here, through the years, there has been a lot of interest on controlled linear sequence polymerization, degree of cross-linking, degree of branching, hyperbranching, and there's even, of course, interest through the years with dendrimers, linear dendrimers, graph systems, and these days a lot of interest on sequence polymerization, different types of supramolecular knots, and so on. And in fact, one of the areas that the flow polymerization setup may lead to is control of these process parameters together with the introduction of monomer, leading to a controlled distribution or product architecture of the polymers that is desired. So by that description, I'm lending this proposition to those who are interested in artificial intelligence or machine learning that coupled with control in flow chemistry and the feedback loop that can be integrated, one can easily imagine the use of AI and ML towards optimizing reactions using a flow chemistry setup. In fact, in the molecular level, we all know this in terms of controlled architectures, controlled sequences, or even living polymerization. So I just listed here a number of controlled chain addition or living polymerization methods that are well known and has been done mostly in the batch, but can actually be done under flow condition reactions. And for example, there has been a lot of studies on simple control of monomer ratio, or monomer initiator, and by controlling the residence time, one is able to isolate products of different molecular weight and control PDI. In fact, a normal free radical polymerization, when done in a flow chemistry setup, actually yields very good polydispersities, whereas those done in batch have larger polydispersities and not so controlled molecular weights. So a simple rule is that the longer the residence time or reaction time, the higher the molecular weight is obtained or yield. And that unprecedented control is quite different from a simple batch mixed feed ratio. So here, for example, you have a mechanistic definition of ATRP, RAF, NMP, and of course, you have other types of living polymerization. So by lending control of the initiation and initiation equilibration process, let's say with a chain transfer agent, or ligand control of, let's say, the active species of copper in ATRP, one is able to couple that control in a flow polymerization setup. So again, a simple rule with flow chemistry is that you can simply control the flow rate and come up with a different molecular weight. So the rule is that lower the flow rate, the higher the molecular weight that is obtained. And usually that type of control is done by monomer feed ratio. But in this case, using a flow chemistry setup, you actually do this control simply by controlling the flow rate. It is also used to control a polymerization sequence, or even the introduction of monomers to form block copolymers. As shown here, one can control the introduction of monomer A and then loop it to another flow reactor, where that product is taken and reacted with monomer B to come out with a simple diblock copolymer of monomer A and B that can be produced continuously using a flow polymerization setup. Other types of flow could be pulse control, continuous flow, and of course the parameters of temperature and pressure. And as I'll show you later, in a simple free radical polymerization, living free radical polymerization, the use of lower temperature or higher temperature control gives an important addition towards the control of the molecular weight as well as yield. So the setup that we use actually is a commercial setup from Thales Nano. So I would like to acknowledge work with them. But there's no reason that you can simply use a flow pump or a pump syringe to control the flow, and as well as produce an isolated or insulated jacket on a column. In fact, if one is familiar with um, HPLC methods, one can adapt simply an HPLC pump to automate the whole process. So one of the first papers we published is in the area of RAF polymerization. In this case, what differentiates it is that we are able to do RAF polymerization with water or water and ethanol. In a normal batch condition, this is not easy, if not subject to other types of side reactions or even gelation. So again, the assumption here is by doing this reaction in a flow setup, we are able to control the environment by which mixing occurs. And as I'll show you, the half-life of the initiator, or rather control of the half-life, has an important implication with respect to controlling the percentage yield and the molecular weight in a continuous manner, as I'll show you. So in this case, we first demonstrated this reaction with the use of a RAF polymerization with a chain transfer agent. That means we have to introduce our initiator, and then the chain transfer agent then allows the reaction to proceed with the monomer that is shown here. So we used essentially a PEG metacrylate monomer or PEGMA. We use a water-soluble AIBN-like initiator. The reaction was done at a higher temperature of 80 to 100 degrees C, pressurized up to 73 bar, and then we control the flow rate. So schematically, what you see here is the reactant or the monomer and initiators are introduced through the pump, goes through the column, and the column itself is pressurized, and you can control the temperature to higher temperatures, and then the control of the flow has a safety valve, which then allows you to obtain the product in a continuous reaction. So I mentioned about half-life and its importance in controlling the reaction. A typical polymerization done in batch, if done with the AIBN-like initiator, has to be done lower than 80 degrees C. And that means that the reaction has to be completed in hours, 2 hours, sometimes 10 hours, in order to isolate a product with a good yield. It's because of the intolerance of the reaction to higher temperatures. However, since we're doing this reaction in a controlled pressurized environment, we can actually heat up the column up to 100 degrees C and achieve a half-life of minutes. In other words, what would have taken hours to complete a reaction can be done in minutes. And this means also, since it's connected to a pump and a continuous flow setup, we can keep this reaction going on until we run out of the monomer or replenish the monomer and produce the product. Now, such is the case that was demonstrated here. Under flow conditions, this reaction produced a controlled yield based on the flow rate. So as you can see here, by controlling the flow rate to 0.2 to zero point 0.5, we actually control the residence time. The lower the flow rate or the higher the residence time, if you see the corresponding conversion and the molecular weight, the result is that you get higher molecular weight with lower flow rates or higher residence time. And simply by controlling the flow rate, one can go from high to low molecular weight. Now, this is usually done in a batch reaction by controlling the monomer feed ratio or by taking the alcohol at specific time periods. But in this case, we have very good control of the molecular weight, very good dispersity, simply by controlling the flow rate. Okay. So that paper was published and others have reported that work, of course. Now, let me demonstrate to you what can be done in a continuous synthesis to produce grafted polymer brushes on a silica microparticle. So in this case, typical grafting of polymers on particles is done in a batch mode where the reaction is done, or the initiator first is grafted on the surface. The polymerization is done by surface-initiated polymerization with the addition of the monomer, and after the reaction, isolating the polymer and separating the unreacted monomers and non-grafted polymers as well. And this can be done sequentially, but in order to switch to a block of polymer, you have to go through this isolation process and then reintroduce the grafted polymer to another reactor or a batch reactor. In the case of flow chemistry polymerization, this is all done continuously. In other words, we don't need to isolate or remove the particles from the column, but rather, after grafting the first block, we can then wash the system and then introduce the next polymer, and in principle, go from A to B to C or A, B, C, so on and so forth, as long as the particle is grafted on, the particle is in the column and the polymers are grafted on the surface. So to demonstrate this work, we first synthesize a chain transfer agent that can be grafted on the surface, as shown in this simple amidation reaction. We then grafted the silane in a flow reactor setup. So as shown here, we introduced this on a bed of microgel, or rather silica particles. that have been packed well in a column. The silica particles by silinization will have the grafted chain transfer agent. And then, of course, after that, we can then do the polymerization of the PEGMA or polyethylene glycol methacrylate homopolymer. So this was first done with PEG-MEMA, and then we switch over to the next monomer after completing the first block by grafting N-isopropyl acrylamide or NIPAM. So this demonstration of a black copolymer was done using a continuous flow polymerization setup. So for example, after this reaction has been done, we did the characterization on the silica particle. So we have differentiation here between the pristine silica gel and then the modified silica containing the chain transfer agent. So clearly, we were able to distinguish the presence of the grafted silanes and grafted thioester bonds. And then after the polymerization, we then did a thermogravimetric analysis to determine the amount of polymer that was grafted on the surface. So for example, as you can see here, a particle in which we graph with different flow times. So as I mentioned earlier, by controlling the flow time or flow rate, one is able to control the grafted molecular weight. So I'm going from 30 minutes to 3 hours. As you can see here, we have increasing weight loss on the grafted silica particle, grafted polymer on the silica particle, meaning the increase in weight loss corresponds to the weight of the polymer that was grafted on the surface. So more weight loss means more polymer was grafted. And as shown here, with the longer residence time of 3 hours, we get higher grafted polymer. The same with controlling actually the concentration. So we can also control the feed ratio, in this case by controlling anywhere from 0.2 to 0.8. The higher amount of monomer translates to greater weight loss or higher amount of grafted polymer. So how did we analyze the polymer molecular weight? We did what we call a degrafting experiment. So after degrafting the polymer from the surface of the silica by simple potassium hydroxide treatment, we then took this isolated polymer and analyzed the molecular weight by GPC. Again, what is shown here is we have a grafted polymer with a higher molecular weight observed from either a longer residence time of the reaction or a higher concentration of the monomer, as shown in this retention volume graph. So higher retention volume, of course, lower retention volume, of course, translates to a higher molecular weight as detected from the GPC. And again, we characterize these blocks by IR as well as thermogravimetric analysis. The blocks showed a higher weight loss as compared to the homopolymer, suggesting the grafting of the second block resulting in more weight loss. And then finally, the GPC between PEG-MEMA and PolyNIPAM was also analyzed by NMR. So the molecular weight as well as the molecular weight distribution between the two blocks are shown here with very good control as well as characterization observed from NMR. Now, just to test actually the wetting properties of the particles that were isolated from the column, what you see here is that the polymer surface is largely hydrophilic on the homopolymer and also on the silica gel or the non-treated material. However, with the addition of NIPAM, which is what we call a LCST behaving polymer, or you simply heat it and it becomes hydrophobic, what we observe here is that by heating it up to 60 degrees Celsius, we see an increase in the contact angle or increase in non-wetting behavior demonstrating that the polynipam does exhibit an LCST behavior, or simply becomes more hydrophobic when heated. Okay. And then another interesting thing is we never observe any gelation using the flow chemistry setup, but we had problems with gelation when we do the same reaction on a batch mode. And that is the gelation is a exhibition of the Tremsdorf effect, or the Norris-Tremsdorf effect, where you have an auto-acceleration simply because the polymer becomes viscous. Now, the last example I have for this talk, and I'll be happy to take questions afterwards, is how we use the setup to control the branching, or the degree of hyperbranching, by use of an enimer, and how we are able to, for example, demonstrate what we call a linear hyperbranch dendrigraph on a particle surface. So again, the same method. We pack the column with the particles. In this case, instead of doing RAF, we did ATRP. So the ATRP silane agent was fixed on the surface, and then we are able to control the introduction of the N-isopropyl acrylamide as a monomer, as well as the introduction of the ATRP enimer, which has a methacrylate group and a brominated, alkyl brominated initiation site that will cause the hyperbranching using the self-condensation effect. So as shown here, we did this under flow polymerization setup. We get very good control on the enimer to monomer ratio, showing that we can control the grafting, the dispersity, the molecular weight by controlling the ratio of the enimer and the monomer. That is, the more enimer we have, the higher the branching, but then the molecular weight, which can also be influenced by the hydrodynamic volume, does not easily track, but rather has to be distinguished by the use, let's say, of a quadruple detector that differentiates viscosity effect, refractive index effect, light scattering, and UV-Vis. So in fact, this paper is still under preparation, but what is clear here is that we are able to differentiate these parameters under flow setup, which is controlled branching. In fact, morphologically from SEM, this shows you the pristine particles before grafting, and then after grafting the polymers on the particle. And we then controlled also the wetting behavior by controlling the pH. So in this case, the higher pH results in a more hydrophobic backbone with the hyperbranch grafted hydrogen polymer, which is observed with these different contact angle measurements at various pHs. And then lastly, the grafting was verified by XPS, or X-ray photoelectron spectroscopy, representing the monomer, which has nitrogen, the unreacted initiation sites, which has the bromine, and of course the carbon, the silica, and oxygen from the particle and the monomer itself. We actually try to see how this type of grafted hyperbranch polymers are able to capture dyes. So the dye here is negatively charged, but then by controlling the charge of the amine group on the surface by protonation, we are able to capture more dyes. So for example, at pH 3, which is a lower pH, that means we have a protonated amine, we are able to capture more of the negatively charged red dye as compared to a higher pH. So hopefully I've shown you the possibilities for flow polymerization setup. Reactions done under these conditions will give you control or unprecedented control on the products, the yield, the sequence, the grafting, as simple as controlling the flow rate, or in the future, in the case of controlled process parameters that include temperature, pressure, or mixing ratios, one is able to continuously produce polymers or materials in this manner. So with that, I'd like to thank you for participating in our webinar series, and I'll be happy to answer any questions. Please contact me through Park or directly from our website, as well as by email. Thank you.
All right, thank you, Dr. Advincula. If there are any questions out there, please type them into the GoToWebinar questions module or raise your hand. Give you guys just a moment to get those in if you have any. All right, I'm not seeing anything at this point. Since this is our last currently scheduled session with Dr. Advincula, I do not have my usual follow-up questions, so I guess we will wrap it up here. Thank you, Dr. Advincula, for the 6 webinars in this year's series. We will be back in 2021 or possibly earlier with more webinar sessions, so stay tuned for more information. If you do have any questions that come to mind after the session ends, please feel free to still submit them, and I will give you my email address shortly. Please consider joining us for or submitting an abstract to participate at the 2020 Nanoscientific Symposium for a Changing World, a virtual conference being held October 14th and 15th, featuring speakers such as Dr. Advincula, giving talks on the nanotechnology research being done today that will help improve our world tomorrow. We are still accepting abstracts for a few remaining short presentation slots, as well as virtual poster session. All accepted abstracts will receive cash awards and be eligible for publication in Nanoscientific Magazine. Submit today at live.parksystems.com/NSCW. Thank you all for joining us for this session. You can find more information about Park Systems, AFM at parksystems.com, and please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions specific to this webinar, feel free to reach out to me directly at richard@parksystems.com. Thanks again for joining us, and stay safe, everyone.